Alright guys, today we are learning how to solve by elimination. This is a continuation of section 3.2, which is solving algebraically. So to solve by elimination, there are a couple steps. The first step is, well, as you would guess, to try to eliminate, and we're eliminating variables. So we'll multiply one or both of the equations by a value to create coefficients that are additive inverses. After that, we'll add and solve for the non-eliminated variable. Once we have that value, we will substitute it into the one of the original equations to determine the other value. So let's work through a couple examples. This is our first example of elimination, our second example in this lesson. We're asked to solve the system. And remember, to solve a system means to find the coordinates where those two lines intersect. So we'll begin by multiplying the first equation by -1 to eliminate the y terms. Right now they both have the same coefficient, but we need one of them to be positive and one of them to be negative. So I chose the first. You could have chosen the second, but that was just what seemed easiest to me. After that, we will add the equations and solve for x. Here is my system after I've multiplied the first equation by -1. As you see, we'll have x is equal to 3. We have eliminated the y term, which is wonderful because we can now move on to our third step and solve for the value of y. I'm taking x equaling 3 and plugging it into the first original equation of my system. So y is equal to -4. That means my solution is the coordinate 3 for the x value and -4 for the y value. We could check that by plugging it into each of our system's equations and finding it to be a true statement. And I'd encourage you to do that now, to pause the video and check that this makes a true statement for each of your equations. All right, let's look at a final example, something a little bit different here. Oh, I should change that to example 3, sorry about that. So we're going to solve this system, and again, we look to multiply because we don't have additive inverses currently. If I take and multiply the second equation by -3, I will have a positive 6y and a negative 6y. And that'll be great because then I can add and solve for x. Here's what my system looks like after multiplying by -3. So -3 times 5 is -15. -3 times 2y, that's going to give me my -6y. And -3 times 1 is -3. 7x minus 15x, that gives me -8x, and -4 and -3 is -7. Solving for x leaves us with x equaling a positive 7 over 8. And it is at this time that I want to show you something you can do so that you don't have to substitute that fraction into one of the originals. We can eliminate again. We're going to go back kind of like to the starting, and instead of eliminating the y's, we're going to eliminate the x's. So looking at our equations, the original equations in our system, if we're going to eliminate the x terms, you'll notice 7 and 5, we can't just multiply one, we're going to have to multiply both. If we multiply the first one by 5 and the second one by -7, then we will have a positive 35x and a negative 35x, and we'll be able to eliminate. Here are our systems after distributing those values to each term. The 35 and the negative 35 will cancel, so for the y terms, when you add those, you're going to have a 16y, and the constant on the other side will be negative 27. And again, we solve. That gives us y equaling negative 27 over 16. We have both our x and our y value, and we didn't have to work much with our fractions, which I'm sure you guys are ecstatic about. That leaves us our solution being 7 over 8 and negative 27 over 16. You know, it's great that we have elimination, because if you would have tried to determine that by looking just at the graph, well, we wouldn't be able to do that. We aren't able to see that graphically, and that's one of the benefits of this method. And that is all that I have for you guys. Thank you very much.